All right, so same instructions. A, B, C, and D from the first problem, right? I want to know local max, where it's going up and where it's going down. I want to know local max, local min. I want to know where it's concave up, concave down. I want to know inflection points, all right? So let's start with part A. Derivative, right? Y'all want to get both derivatives now? First derivative. How am I going to take derivative of that? What's that? Product rule, right? So derivative first one times second plus derivative second one times the first, right? Because the derivative natural log of x is 1 over x. Actually, I was pretty happy about the class's performance on derivatives on this test. The things that most people struggled with, word problems, okay, as expected, and then also some of the stuff with limits, L'Hopital's rule, things like that. But as far as derivatives are concerned, I feel like a lot of you are really getting the whole idea of like product rule, quotient rule, chain rule down, which is good. All right, so there's our derivative, right? Now let's clean this up because there's a little bit of cleaning up we can do. This right here, right, that's the same as x squared over x. And so you can just cancel out one of the x's and that's just x. So my derivative is 2x natural log x plus x. Okay, there's my first derivative. Let's take the derivative of that. So my second derivative, I'm going to have a product rule right here, right? There's a product between these two, and then that plus x is by itself. I can just differentiate that on its own. So when I do the product rule here, what do I get? Derivative this, 2, and then 2 times ln x, plus now derivative ln x, 1 over x, and then times 2x. I'm done with product rule, right? Plus derivative x, 1, plus 1. And we are going to clean this up now. What does this become? 2, right? That's just 2. And I can add 1 at the end, right? 2 plus 1 is 3. So I just get 2 natural log x plus 3. That's my second derivative. This is my first derivative. Are we good? All right. What do we do now? Find the critical points. We have to figure out where the first derivative is 0, where does it not exist, right? So I want to know where's the derivatives, first derivative 0. Where does the first derivative not exist? All right, let's do the set it to 0 first. Got to solve that equation. Anybody see anything? X, they both have an x in them, right? GCF, greatest common factor. We can pull an x out of both terms. There's an x here and an x here. Not this x. That x is trapped in the log. So pull those two x's out, or pull the x out. You'll be left with 2 natural log x plus 1 equals 0. And now you have two things that multiply to be 0. So set them each equal to 0. So set that equal to 0. Set 2 natural log x plus 1 equal to 0 as well. The first one is already solved. This is done. X is 0. The other one, we need to solve for x, which is weird because it's in a natural log, right? So let's just follow me through this. First thing I'm going to do, move the 1 to the other side, make it -1. Then I'm going to divide both sides by 2. And now we're back in college algebra. I want to get x. It's trapped in a log. natural log, how do you kill off a natural log? The exponential, e to the x. So to kill off ln x, you have to bring in e to the x. So I'm going to do e to natural log x, e to the negative 1/2. And what that gives me on the left, e to the natural log of x is x, and then the right side is e to the negative 1/2, which is just a number. And we could use our calculator. If you have a calculator, I don't have mine with me. Somebody do e to the negative 1/2, or you could do e to the negative 0.5 if you want. Somebody tell me what that is approximately. What is it? 0.606? 0.607. 0.607. Okay, good enough. 0.61 would be fine. Anybody else get that? Yes? All right. We have two places where the first derivative is 0. Now, I still need to figure out where the derivative doesn't exist. All right, so what about the derivative? Look at this derivative. Are there any values that you cannot plug in for x? Cannot plug 0 in. Think about the natural log function. What does the natural log function look like? Looks like that, right? That's what natural log of x looks like. This natural log function is not defined for negative numbers. You cannot plug negatives into logs. This goes back to college algebra, right? You cannot plug a negative into a log, and you cannot plug in 0 into a log. Therefore, over here, I know that x has to be greater than or equal to 0, right? For this derivative to work, right here, x has to be greater than or equal to 0, doesn't it? But look at the original function. Don't we have the same domain for this? Look at the domain of this. X must be greater than or equal to 0, right? Again, we have a natural log in there. So I'm sorry, not equal. Did I put equal? Take the equal out. That's a mistake. I don't know why. I just said greater than 0 and I put equal here, right? You cannot plug 0 in here and you can't plug negative numbers in here. So your domain is everything greater than 0. Here, same thing. Because the derivative has a natural log in it, you have to throw out anything that's negative and anything that's 0. So as long as we are using positive numbers, as long as the numbers are positive, do you all agree that this is defined? As long as x is positive, this is okay, right? So we should have no issues from this. There's nothing that causes it to not exist because our original domain restricts us to positive numbers to begin with. Which means we only have at the end 2 critical numbers. And so what am I going to do with those?
Question?
Yes?
X has to be greater than 0. Is 0 a critical number?
No, because it's not in the domain of the original function. So to be a critical number, that number must be in the domain of the original function.
My question was,
Oh.
we only have one critical
Oh, this one right here. I see what you're saying here. This one. So yeah, we would throw this one out because it's at the end of the interval and it's not included. So we're going to do a number line right now, right? So when I do my number line, what do I want to erase? I think I want to erase up here. When I draw my number line, what's being stated here is that this is not a critical number. Even though it solves this, it sets it equal to 0, right? Because the domain of the original function is greater than 0, strictly greater, your critical number has to be in that domain, which x is not, 0 is not in the domain. So we throw this one out. This is the only one we have. All right, so that one I'm going to put on number line 0.607. And now I have to pick test points. Now this is actually important because when you pick your test point to the left of this, you can't pick anything from 0 on. It's got to be between 0 and here. So what test point would you like? 0.5? Is that what I heard? And then something to the right? How about 1? And where do those get plugged in? Into the derivative. So let's plug those in. I'm going to do f prime of 0.5, and I'm going to do f prime of 1. So when I do those, I'm going to do the one that's easier for me to do right now. If I plug in 1, I can plug 1 into this pretty easily, right? It's going to be 2 times 1 times natural log of 1 plus 1. And the reason I like that is because this right here, again, college algebra, the natural log of 1 is 0. So that, I know that that's all 0 here. So my answer is 1, which is a positive number, right? So at 1, when I plug that test point into the derivative, I get a positive answer that tells me my original function goes up here. I still have to plug 0.5 into the derivative. And if you do that, you should get a negative. I don't know, though. You have to check it. Did you get, what'd you get? Negative 0.9. Okay, so it is negative. Negative 0.19. So it's a negative number. What does that tell me my original function is doing here? Going down. All right, questions? Part B. Or no, we haven't answered part A. Part A, here's our answer. Where's this function going up? To the right of that, right? To the right of this? So I'm going to write it this way. E to the negative 1/2 to infinity. So I could put 0.607 here, but I'm going to put the exact number, e to the negative 1/2. Isn't that where we got that from? So from there to the right forever, it's going up. And now be careful here. Where's it going down? Be careful. Be careful. We can only be talking about x values to the right of 0, right? You can't plug 0, you can't plug any negatives. So this function can only be going down between 0 and e to the negative 1/2. So there's almost like over here 0, right? Here's 0. None of that is included, right? You can't include any of that in your picture. Or in your graph, or in your function, I should say. Yes?
So if we have like so for instance this problem in LN, so we
Yes.
don't know the domain.
Yes.
We have another problem like with log or something like where we didn't necessarily know the explicit domain. Like, well, A, would we ever have
Knowing the domain is going to be an important aspect of these problems. We're going to have to know the domains.
so every problem we get, we'll always be able to find domain.
We should be able to, yes. Some of them are harder than others. This one requires that you remember the domain of the natural log function. All right. That's part A. Part B. Local max. Local min. Do we have a local max? What do you think? Local max? No, right? It never goes up and then back down. Never goes up. So none, right? Do we have a local min? Does it ever go down and up? Yes. It happens here at x equals e to the negative 1/2. And now if I wanted to know the value, I'd have to take that number and plug it into the original function, which I'll do on my on the computer here in a second. All right, let's move on to the second derivative and do the same thing, right? So for the second derivative, the concavity, my second derivative, I need to figure out where my second derivative is 0. I need to figure out where the second derivative doesn't exist. Start with the second derivative 0. So here's the second derivative, 2 natural log x plus 3. Set that equal to 0. And I can do the same thing I did just a second ago. I can subtract 3 on both sides. I can divide both sides by 2. And I can bring in the e to kill off the natural log. So I get e to the negative 3 halves instead of negative 1 half. And on our calculators, that's approximately .223? Approximately 0.223. We'll verify all this when we look at the graph in a minute. All right, and that definitely lives, you know, it's a positive number. Domain of this is positive numbers, so this is a critical number for sure. And then what about where it doesn't exist? Any issues here? Well, again, that has to be, the x has to be greater than 0, right? But that's already our domain restriction, so we have nothing from this. So we only have one critical number. Here it is. I put it on number line, 223. I pick a test point here and here. This test point I'm going to use 0.1. This test point I'm going to use 1. Remember, I have to pick a positive number. That's why I'm not picking 0, because I can't plug 0 in. If I plug in 1 into that derivative, if I plug in 1, we got to plug in 0.1, and we got to plug in 1 into the second derivative. If I plug 1 into this, natural log of 1 is 0. That kills that. I just get a 3. So this should just be positive. Ah, wrong one. This should be positive. And then negative. If someone could please check for me that when you plug 0.1 into this, and then multiply by 2 and add 3, tell me what you get. I keep leaving my calculator at home, or on my desk. Times. I get a negative. Yes. Negative 1.6? Okay. Yeah, negative 1.61. All we care about is negative, right? That's all we care about. It's negative, which means we are concave down here, concave up here. And so I think I'm ready to put all this stuff together, get my answer here. So where's the function concave up? Where's the function concave down? And then let's see if I have any inflection points. So we're concave up to the right of e to the negative 3 halves. Right? Over here, we're concave up. We're concave down from 0 to e to the negative 3 halves. And again, you could, instead of doing this, you could put the 0.223 or whatever we had. Do we have any inflection points? Where? At x equals 0.223, right? Or e to the negative 3 halves. Desmos, let's graph it. So it was x squared times natural log x. There's the graph. There's the graph. Notice the graph only exists from 0 on, right? Also, we got a lot of interesting things happening here. we had no local max, right? Do y'all see there's no local max here? Where was our local min? At where? What was it was e to the, so I'm going to go e raised to the negative 0.5 here. What's wrong? Oh, I want to graph it. There it is. All right, I'm going to exaggerate this so you can see it a little bit better, maybe. There we go. That exaggerates it for you. So do y'all see we have that? That's a local minimum, right? It's happening right there. And then it's decreasing to the left of that and increasing to the right. And then we had an inflection, right? We had an inflection, and that was happening. Well, I don't see. Do you see concave up and concave down? Hard to see it. Let me do the inflection. Let me graph the inflection point first. The inflection point was this one. There. So the green is our inflection point. Do you buy it? Does it look like an inflection point to you? If I zoom in the right way, does that look like frown turns to smile? Right? Frown turns to smile. Concave down, concave up. Now look, I'm going to go back to the standard graph, the way the computer would graph this. You're not, if a computer graphs that, right, you're not seeing inflection here, are you? It's hard to see that there's inflection in there. It's hard to see concave down. You might look at this initially and think it's all smile, right? If you just rely on that graph, you would have to really get in here and analyze it to really see that you had an inflection point. But our calculus told us we should have one, right? Okay. What are y'all thinking? How are y'all feeling here? Yeah? I've shown you two examples, a polynomial and then something with a log. I mean, really the whole idea here is that we should be able to handle any function. As long as we can take two derivatives and set them equal to 0, like there's no restriction on what we should be able to do. Let me go back to the book and let me see if there's anything else we want to look at. Yeah, I think that's it for that one. Let me, no. All right, we're going to do number 20 here. So I'm going to call it f of x instead of y. F of x equals square root of x squared plus x minus x. All right, before you get started, I would like for us to, we're going to shift gears a little bit here, all right? The next section in our chapter is called curve sketching. And so this is actually a section we could spend like 3 weeks on it, curve sketching. And what it does is it says, okay, let's bring everything together now. College algebra, pre-cal, Cal 1, let's bring everything together and let's use it to get very accurate, precise graphs of functions by hand. So using all the tools that we have at our disposal to draw very, very precise pictures of functions, assuming we wouldn't have a computer to do it. So my feeling on this is that we do have computers to do this, right? So do we really want to invest that much time and energy doing something that that technology can help us do. And I don't think we should, all right? So this is something that has adapted over the years that I've been teaching this. If you would have asked me back in the early 2000s, I'd be like, no, you need to do this by hand, because you couldn't go to a website very easily and get a picture. But because we can, I'm going to do one example of how the curve sketching technique works so that you've seen it, but I'm not going to test you on it. That doesn't mean turn me off and just, forget what I'm doing up here, because while I'm doing it, I'm going to be doing the steps that we just did. Right? Everything we just did on the previous two examples, I'm going to have to do while I'm doing this problem. All right? All right, so here's how I would go about trying to sketch this. All right? First thing I would do is I just find the domain of this function. So what's the domain? Well, I have to make sure that what's underneath the root, let's start the clock, 10:05. Let's see if we can finish this problem by the end of class. All right? That's how long it's going to take us to do this problem. So maybe, I don't know, I'll try and move fast. So we look at this and we say, okay, is there anything here that would cause us to have a negative under that root, right? So I need this. I need x squared plus x to be greater than 0, right? That's what I need. I need what's under that root to be greater than 0, or else this thing is not defined. This is called anyone know what this is called? What is that? Okay, what is that? Symbol. A what symbol? Is it an equal sign? No. Greater than, right? We call those inequalities. This is a quadratic inequality. And so, like I just said, this whole method I'm about to show you, it brings everything together. Where do we learn to solve quadratic inequalities? College algebra. How do you do it? Well, do you know? I know. Do you know? First, you take it and set it equal to 0. So I'm about to do this right now. I'm doing a different color because I'm doing this. This right here is called a quadratic inequality. All right, so I take it and I set it equal to 0 first, right? Remember how we came into this class and we just jumped right into limits? We just went right to limits, right? I didn't spend 2 weeks reviewing college algebra, okay? Because I just don't think in Cal 1 we should spend 2 weeks reviewing college algebra, but now I need it. I need you to know how to do this. So this, you can just pull a GCF, set each equal to 0, you get 2 answers. Okay, we get 2 answers, right? Those are not our answers. Okay, this is just the answer to the blue, to the quadratic equation, right? So to solve a quadratic inequality, we first turn it into an equation, we get our solutions. What do you do after that? No? You draw a number line. You put those 2 answers. You break up the number line. You pick test points. And you plug those test points into the inequality and see if it's true or false. So let's plug -2 in here. What happens if I plug -2 into that? What do you get? -2 squared is 4 plus -2 is 2. Is 2 bigger than 0? Yes. Plug in, what's the number here? -1/2? Plug -1/2 in there. What happens if you put -1/2 and square it? Nope, that's if you're adding it. You get, so we're doing, let me do it. -1/2 squared plus -1/2. -1/2 squared is 1/4. Then this is -1/2. What happens if you take 1/4 and take away a half? Is it positive or negative? Negative, right? So is that true? If I plug -1/2 in here, is it bigger than 0? No, you said it was negative, right? So it's not bigger than 0. So that doesn't work. And then you plug in, let's say 1, and you plug 1 in there. 1 squared plus 1, is that bigger than 0? Yes. So what is the domain of this function? Stuff to the left of -1 and stuff to the right of 0. That's our domain. So domain is, I'll do it here. Domain is stuff to the left of -1 and then stuff to the right of 0. That's the first step. Now, there's a bunch of other things that I could do right now. And like I said, I'm showing you this method, but I'm not going to test you on it. I want you to know, but at least see it once. The next thing I would do is I would ask myself, is there any symmetry in the problem? Is this an even function or an odd function? That goes back to pre-cal. It also goes back to college algebra. Even functions are reflections over the y-axis. Odd functions are reflections over the origin, which means a double reflection. There's a way to check if this is even or odd. It's neither. I know that because I can tell. But I'm not going to go through it, but I'm just telling you that's something, if we were trying to sketch this by hand, I'd be thinking about symmetry now. I would also ask, are there any asymptotes? Vertical asymptotes, horizontal asymptotes. So to do that, I would take limits and let x go to infinity and try and figure out what happens. So you start getting all these like ideas of what this thing's going to look like. You know what its domain is. You know if you have any like symmetries in terms of like a reflection. And then you finally get to the calculus part of the problem. All right? Oh, you know what? Let me do one thing. I will show you one other thing we should look at. Are there any x-intercepts? Does this graph ever hit the x-axis? Right? It would be nice to know if it hits the x-axis anywhere. How do you find the x-intercepts of a function? Set it equal to 0. And what is that? Do you know what kind of equation that is? College algebra, math 1414. It's been a long time. This is what makes being an engineer and being these STEM majors, this is what makes being that so difficult. There's so many things you have to know. Like just because you pass college algebra doesn't mean that you are ready to be an engineer. You have to remember it too. Like you have to be able to recall all these things that just will continue to follow through with you. All right? I'm not trying to discourage you. I'm just trying to be honest and open with you and like be like, hey, you've got to know these things. These are the things you will struggle with and continue to struggle with the rest of your math. Even if your calculus is good, you have to know how to solve that equation. It's a radical equation from math 1414. And to solve a radical equation, you must, what? You're going to have to square at some point. But the first step is to isolate the radical. You get the radical by itself on one side of the equation first. I mean, I believe it's all in there. Everyone's got, like the information is in there, but you have to be able to like dig it up and crank it out. So I isolate the root. Now I square both sides, okay? What happens if I square this side? What do I get? X squared plus x. And what happens if you square this side? X squared. Okay. Hey, that's actually not that bad, right? Because now, what can I do here? Subtract x squared on both sides?